So let's say that we have a random sample, x1 through xn. An arbitrary function of a random sample is called a statistic. The most famous statistic is the sample mean, but that is just one example. So for a statistic, we can do any function of this random sample. Just like the sample mean, a statistic will be a random variable, as we do not know the value of the statistic until we perform the experiment and we know the values of the x variables. Other common statistics are the sample variance, and when you have a random sample of both x and y data, then we have the sample covariance. Let's say that the random variables in the random sample have a distribution which depends on some unknown parameter, which I'm going to call mu. For a concrete example, I could have a random sample where xi was IID normal, independent, identically distributed, all of them following a normal distribution, all of them having an expected value mu, which is not known. And in this example, let's say that we know that the variance is 1, so that there is only one unknown parameter. Mu is the only missing piece of information here. If I had known mu, then I would know that, for example, x1 followed a normal distribution. I would know its expected value and its variance. And if it's normal, that completely specifies the distribution of x1. So in that case, I would know everything there is to know about the x1. And the same thing goes for all the other x variables. So the unknown parameter mu is the only thing that holds us from knowing everything about the random sample. The purpose of statistics is then to use the random sample to create the best guess possible for mu. We say that we try to estimate mu using the random sample. We also use the following terminology. So an estimator is then defined as so most importantly, an estimator is really a statistic. That is, an estimator must be some function of the random sample. And again, that means that an estimator must be a random variable whose value is only known after we perform the experiment. But it's only when we use a statistic for the specific purpose of estimating an unknown parameter that we call the statistic an estimator. So all estimators are statistics, but not all statistics are estimators. The most common estimator for an unknown expected value is the sample mean. So the sample mean is an estimator of mu. In this particular example, it will be the best estimator of mu pretty much independently of any reasonable definition of what we mean by best. So we can generalize this and call it the typical statistical problem. I have a random sample, which is just a bunch of random variables. These random variables, they all depend on a bunch of unknown parameters. Just like in the previous example where the random variables depended on the unknown expected value. But this can be much more general. So I could actually have several unknown parameters. Could call it mu1 to, could say we have k unknown parameters. So what we try to do in statistics is then to find as many estimators. Find k estimators. In general, we can call them T1 through Tk, where we use T1 to estimate mu1 and so on. The parameters then sometimes have an interpretation that's meaningful to us. For example, one parameter could describe the relationship between education and salaries. And once we've collected data on education and salaries, we may be able to say something about the relationship between education and salary. Here is a simple illustration of the example we used. So here n is equal to 10. Each random variable is drawn from a normal distribution. The expected value is 0 and the variance is 1. Now, of course, that's behind the scenes. In statistics, all we are given is this actual data. That is, in statistics, I can't really click on a cell like this and read how it's generated. All I have is this data, and what I want to do is to estimate the expected value, which we know is 0. And the estimate that we use is the average, the sample average. So with this particular data, my estimate of the expected value would be 0.11, which is not too bad considering that the true value is 0. How well we do? Well, that depends on luck. In this case, for example, we did much worse. Our estimate would be minus 0.72. Here, a lot better. And sometimes we can get really, really unlucky and get something terrible. Or we can get really, really lucky, like in this case, and have an estimate which is really good. It all depends on chance. All consistent with an estimator being a random variable, while the expected value, the thing we're trying to estimate, is a constant. Unfortunately, not known to us.